Welcome to this talk on gravitational waves from low-scale cosmic strings. This is a project I've been working on in collaboration with Kai Schmitz. Before I come to the actual topic of my talk, let me give a brief review of cosmic strings. For this, we need to consider a spontaneous symmetry breaking in the early universe. If the associated phase transition occurs in such a way that the corresponding vacuum, called M here, is not simply connected, which is for example the case if we break a U1 symmetry, then tube-like regions in space will occur in which the transition from the old vacuum to the new vacuum is topologically forbidden. These tubes are called cosmic strings. This means cosmic strings are one-dimensional field configurations in which the symmetry is unbroken and the vacuum therefore is not assumed. Strings are described in terms of their energy per unit length, the so-called string tension mu, which is here rescaled with Newton's constant g to make it dimensionless. This string tension goes like the symmetry breaking scale squared and is typically larger than 10 to the minus 34. Another important quantity to describe strings is the string width, going like 1 over the symmetry breaking scale, and this is typically smaller than a thousandth of a proton radius. In cosmology, we are interested in the dynamics of these strings on scales much larger than their width. Therefore, we can, to a very good approximation, neglect their internal structure and approximate them as effectively one-dimensional objects. The dynamics of the strings is then described in terms of the Nambu-Goto action, and the only free remaining parameter is a string tension g mu. During a phase transition, we don't obtain a single cosmic string, but rather order one cosmic string per Hubble volume. These strings are very long, typically larger than a Hubble length or infinitely long. These long strings start then to move around, interact with each other and also with themselves, and in this process they chop off sub-Hubble length string loops. These loops will start to oscillate due to their tension and then decay via the emission of gravitational radiation. These loop oscillations occur with a set of discrete frequencies, namely as multiples of a fundamental frequency, which is simply given as 2 over the current length of the string. The deformation of a string loop due to the first 3 oscillation modes are illustrated in this figure here on the left-hand side. Accordingly, if we look at the corresponding gravitational wave spectrum, denoted from now on omega, we can take the spectrum and decompose it into the contributions from the different oscillation modes. An important thing to note, if one carries this calculation out in detail, is that the contribution from the kth oscillation mode can be expressed in terms of the fundamental mode contribution by rescaling its argument like this and multiplying with a prefactor pk that decreases with increasing mode number. Due to this feature, it is henceforth enough to focus on the fundamental mode only, which has a frequency 2 over the length of the string, and draw conclusions on the full spectrum only in the very end. What we also need to know is that the total power emitted from these string loops into gravitational radiation scales like g mu squared. The prefactor gamma was fixed in numerical simulations to be of order 50. We also know that a string loop has an energy which is simply the string tension times its length. From these two expressions, we can directly calculate how a loop shrinks due to the emission of gravitational waves over time. If a loop had at time t prime a length L of t prime, then it will have at time t a length L of t given by this expression here. The last important thing to note to make the main argument of this talk is that the distribution of the production length of string loops at a given time is sharply peaked around a fixed fraction of the Hubble length. Therefore, we can say to a very good approximation that at a given cosmic time t, loops are produced with a single length L star proportional to cosmic time. The proportionality constant alpha was fixed in simulations to be around 0.05. This tells us directly that the smallest loops are those produced at the earliest times. If we say that T_INI is a time when loop production becomes significant, then the smallest loop production length will be L_INI, given by this expression here. These string loops produced at the earliest times are also those that have the longest time to decay. So if we follow their length evolution over time until today, this will set the smallest string loop length scale that has ever been around, and we call it L_min. Typically, one considers the case that these earliest string loops have decayed a long time ago, so L_min is equal to 0. For this talk, we are, however, rather interested in the case where the strings have not decayed yet and L_min is larger than 0. To see how this can be achieved, let's look at the figure here on the right-hand side. On the left part of this figure, we have the case A, where we have an initial time T_INI A and a string tangent μA. The loops produced at this time T_INI A will then decay over time, and we consider here the case that they have fully evaporated at time T0 today. On the right-hand side, on the other hand, we have a string tangent that is smaller, and we start with a significant loop production at a later time, which means that the initial loops are from the beginning larger. And in this case, it is possible to find that these initial loops have actually not decayed until today. From this expression here, one can see this also directly, namely L_min is larger than 0 if we make either L_INI large enough or if we make Gmu small enough. Let's now see what this means for the gravitational wave spectra. If strings have not decayed until today, and accordingly L_min is larger than 0, then there must exist a maximum frequency in the fundamental spectrum above which the spectrum drops strictly to 0. We call this frequency the cutoff frequency, which is simply given as 2 over the minimum length. To see this a bit better, let's look at the corresponding gravitational wave spectra. So what we have here is a gravitational wave spectrum, omega of f, as a function of the gravitational wave frequency f in hertz. In the standard case, which is usually considered in the literature, where we don't have such a cutoff frequency, in the regime where we go to very large frequencies, the spectrum does not drop strictly to 0, but goes simply like 1 over f. In the case I want to consider in this talk, where we have such a cutoff frequency, shown here on the right-hand side at about 0.4 Hz, the spectrum rises at low frequencies, reaches a peak, and then drops sharply to 0 as it reaches the cutoff frequency. As we saw before, we can arrive at this case where we have such a cutoff frequency if we consider large initial loop length, L_INI, or if we make the decay into gravitational radiation inefficient, which is the case if we go to low string tangents. Instead of phrasing the criterion L_min larger 0, written out here, in terms of an initial time, T_INI, we can also phrase it in terms of an initial temperature, T_INI. The criterion becomes then that this initial temperature must be smaller than a certain cutoff temperature given by the expression here. To illustrate this a bit better, let's look at the corresponding parameter space. Here we have the temperature T in GeV versus the string tangent Gmu. The cutoff temperature is given by this blue line. And if we are in the part of parameter space above the cutoff temperature, then we will obtain the standard gravitational wave spectrum, which has no cutoff frequency and extends to arbitrarily large frequencies. If we are below this blue line, below this cutoff temperature, then we will have the case where our gravitational wave spectrum from the fundamental oscillation mode contains a cutoff frequency and drops strictly to 0 above. So everything below this blue line is what we are interested in the remainder of this talk. As you can see, there are many more lines in this plot, and I want to explain what they mean and where they come from in the following. Let's start with the formation cutoff. String loops can, of course, only start to oscillate and produce gravitational radiation once the string network has formed. This happens roughly at a temperature T-form given by this black line here in the plot. This means that the initial temperature must be smaller than this formation temperature, since otherwise there are simply no strings around. Next, we have to take thermal friction into account. After the production of the strings, they cannot simply move freely around, but they interact with the surrounding plasma. This strongly dampens the string motion and therefore the production of string loops and therefore also the emission of gravitational waves. We need therefore to consider times when the thermal friction has become subdominant in comparison to the Hubble friction, and this happens roughly at a temperature T-fric given by this orange line here. Finally, strings can not only decay by gravitational radiation, but also via the emission of particle radiation. The decay into particle radiation is dominant for small loops. Therefore, we need to consider initial temperatures such that the initial length of the loops has already become large enough such that gravitational radiation is the dominant decay channel. This happens at a temperature T-rad, which depends on the microstructure of the string. If the microstructure is purely due to cusps, then this radiation cutoff will correspond to the red line here. If it's only due to kinks, then the cutoff will correspond to this orange line we have here. The remaining interesting part of parameter space that I want to consider in the following is everything between this light orange, this dark orange, this blue, and this red curve. For this interesting part of parameter space, we have calculated for 4 benchmark points, 1, 2, 3, and 4, the gravitational wave spectra fully numerically. These spectra, containing contributions not only from the first, but from the first 100,000 modes, are shown in the plot here on the right-hand side. The spectra are labeled according to the benchmark points 1, 2, 3, and 4. On top of this, we can see the sensitivity curves of different future experiments. I want to point out 2 things here. First of all, despite of the low string tangents that we consider, which are typically associated with very low gravitational wave spectrum amplitudes, these gravitational waves can in principle be measured in future experiments such as DECIGO or BBO. The second thing I want to point out is that these full spectra are qualitatively very different from the standard case. In particular, we get an oscillatory feature around the peak of the spectrum, as you can see here. To understand where this oscillatory feature comes from, let's zoom in on the peak region of the spectrum corresponding to benchmark point 2. This zoomed in version can now be seen in the plot we have here. On top, we see again as a solid blue line the total spectrum corresponding to benchmark point 2. We can understand where this oscillatory feature comes from if we remind ourselves that the full spectrum is calculated by summing over the contributions from the different oscillation modes, and that the contribution to the kth oscillation mode is obtained by taking the fundamental mode, shifting it to larger frequencies and to lower amplitudes. What we see in the plot below the total spectrum as gray solid lines are the different mode contributions. First of all, we have here the fundamental mode with the cutoff frequency given by this dashed line here. To obtain now the contribution from the second oscillation mode, we have to shift the fundamental mode contribution to 2 times the frequency and lower amplitudes, and we obtain this curve here with a cutoff frequency at 2 times f cut. Going on like this, we obtain for the third oscillation mode a cutoff at 3 times f cut, for the fourth mode a cutoff at 4 times f cut, and so on. Every time one of the different modes drops out of the sum contributing to the full spectrum, we get a dip in the total spectrum. This means these dips in the total spectrum occur at multiples of the cutoff frequency f cut, which is here in our benchmark scenario at about 0.4 Hz. Finally, you might wonder how strongly this new oscillatory feature in the spectrum depends on the assumptions we made. One of the central points that could have an influence is that we assumed that at cosmic time t, all loops are produced with the same length L star proportional to cosmic time t, where we took this proportionality constant here alpha to be 0.05. In reality, we have of course a distribution of initial loop length that has non-vanishing variance. The initial length distribution one finds in numerical simulations can be well fitted by a Gaussian in the logarithm of the scaling variable with mean value of -3 and a standard deviation of 0.14. Taking this into account in our considerations, we calculated again the full numerical spectra and found what you can see here on the right-hand side. On top, in the upper panel, we have again the gravitational wave spectrum as a function of the gravitational wave frequency in Hertz, and below the corresponding spectral index as a function of the frequency. For all the spectra we calculated, we took nu to be -3, corresponding to alpha 0.05, and standard deviations 0.02, 0.04, 0.08, and 0.16. The central message of this plot is that even for the largest standard deviation we consider here, 0.16, the oscillatory feature survives and might be detected in future experiments. With this, let me come to the conclusion. What we have found here is a new feature of the gravitational wave spectrum from cosmic strings that arises if none of the string loops ever formed have fully decayed yet. This is the case if we consider small string tangents and therefore an inefficient decay of the loops into gravitational radiation, and large initial loop length corresponding to low initial temperatures. In the fundamental spectrum, this leads to a cutoff frequency above which the fundamental spectrum drops strictly to 0. In the full spectrum, we get from this a distinct feature, namely an oscillatory shape of the spectrum with dips at multiples of the frequency of the first dip. If you are interested in more details or related considerations, please take a look at our paper on arXiv. Thanks for watching.